Dave, thank you for joining us. We're going to spend about 30 minutes in a fireside style chat. I wanted to start first by thanking you for writing this book. I got my copy right here. As a computer scientist and an engineer and also an engineering leader, there were tons of insights that I got out of this book. So I just wanted to say thank you. It's a great read, and I learned so much from it already. I want to start off, one of the things that you talk about a fair bit in the book is the DORA metrics. So I wanted to start off a little bit on this theme of like measuring efficiency for software teams, and starting with the DORA metrics. It's pretty clear from the book and your writing that you hold the work done by that team in pretty high regard. The sense that I get is that the metrics are, on track, something that is forward progress in terms of the way that we measure engineering efficiency. What are your thoughts on the metrics themselves? Are there, as someone who's been in the practice of applying them to the management of a team, what are your thoughts on the metrics in the DORA report?
Well, first, thank you for liking my book. but yeah, I'm a big fan of the DORA metrics. Actually, I feel kind of privileged that they asked me to write a section in this year's report, which I did. I think that the DORA metrics represent a step forward in our discipline. I've come to believe that one of the things that distinguishes an engineering approach from, say, a craft-based approach to software development is measurement, but also the ability to kind of figure out the difference between good ideas and bad ideas. If you kind of think about what engineering really is, engineering doesn't give us any guarantees that we're going to succeed, but it's going to eliminate some ideas that are less likely to succeed. That's, in general, I think, philosophically, what engineering kind of does. It kind of rules out the dumb stuff and lets us focus more clearly on the stuff that gives us a chance of succeeding. And I think that the DORA metrics do that. They are not going to guarantee you success. There is no guarantee of success. But if you use those metrics intelligently as a tool, I think that they significantly amplify our chances of success by ruling out some dumb ideas. So fundamentally, the DORA metrics, just to state them in case there's anybody here that's not familiar with those, they're based on two ideas: measuring stability and throughput. Stability is a measure of the quality of our systems. It's measured by the defect failure rate, the rate at which you introduce defects every time you change the system, and the time to recover from those systems. So those are the measures of stability, they're measures of quality. That tells us something important about the quality of their work. Throughput is a measure of the efficiency with which we can deliver work at that quality. So throughput is based on measuring the cycle time, the lead time from kind of commit to releasable, and the frequency with which we exercise that, how many times we actually get those changes out into production. And both of those are really a kind of sideways measure of the batch size of the way that we do work. So the pressure for the DORA metrics to get a good score on both of those metrics, which is the goal, not to prefer one over the other, but to get a good score on both of those metrics, you've got to be working with high quality, and you've got to be working in small steps. And those seem to be pretty much foundational ideas to me in terms of being able to create great software. So I think that they matter, and I think that they kind of this is doing the people that came up with them a disservice, but they almost seem like it's an accident that they got to this really deep stuff. I think it probably wasn't. They were thinking more. They were more thoughtful than that. But I think in part it came to it in terms of trying to think about how you could measure the impact of continuous delivery. I think that at least is in the back of the minds. If I'm honest, talking like a physicist, that's not a good route to good science. So, preferring a solution ahead of time. But I think that that's maybe how they got there. But But I think that they have got to something important, because these are difficult to cheat if you take them both together. That the ways in which I've seen them fail is that where a team either misreads them completely and reinterprets them and doesn't do what they actually say. I saw one team that just changed failure rate to bug count. That's not the same thing, because it's failure rate over time kind of thing. There's a different thing. So there are ways of cheating them like that. But if you take them as read, the other failure is to prefer one of the others. Okay, and the one that nearly everybody goes for is, okay, let's go for the throughput and ignore the quality. And what that means is that over time you're going to go slower and slower and slower, and so you've screwed throughput as well. And so I think that they're this really clever, intelligent combination of metrics that are universally applicable to software. And if you optimize to improve your scores on both of those things, you're likely to get to a good outcome. It's going to drive you in a good direction. And you work to optimize those things, and then other things come in. Oh, well, if I need to be able to update the rate at which I can deliver changes in smaller steps, I've got to make my testing more efficiently. So I've got to improve the automation of my testing. If I want to be able to make changes and get that fast feedback, I've got to change the way that I work so that I can evaluate my changes more efficiently and more quickly. And that has knock-on implications for being able to then release change into production more frequently too, and get into things like feature flags and those sorts of ideas too, to facilitate that. So there's an awful lot of these ideas that kind of fall out from these principles that we start with. So if the principle is to be able to create high quality software quickly, then, and that's what we start by measuring, we're going to get an awful lot of good outcomes. So I'm a big believer in the DORA metrics, and I think they've moved us as an industry significantly forward in terms of being able to rule out bad ideas. So we can say with some sense of authority things like a change approval board slows things down and therefore works against quality. I mean, they make the people involved in the DORA metrics measured that impact. They know that to be true. So this is quite a big deal in my view.
Yeah. What else is it about the DORA metrics that make them more effective than like the previous iterations of like engineering metrics? I'm talking about things like like just raw test case coverage or branch coverage, or even things like cyclomatic complexity, or like other measures that came out. Those were kind of like decades old ideas that really just didn't catch on and didn't seem to be highly correlated with effective software development practices.
I think that the significant there's a category difference between most of those other metrics and the DORA metrics, in that the DORA metrics measure outcomes. Now, they don't measure all of the outcomes that matter, but they're measuring outcomes of our development process rather than particular steps in it. So if you say something like cyclomatic complexity, you're looking at some technical detail of the fact. Actually, in terms of the business impact, the cyclomatic complexity can have an impact in terms of the maintainability of your code, but users don't care about that. Businesses don't care about that, those sorts of things. So I think that these are better measures because they're outcome based. And I think that's one aspect to them. And the other thing is the DORA metrics are part of a broader picture of work to try and understand better what works in software development and what doesn't. The people behind the DORA metrics have data that correlates good scores on these measures with real outcomes almost across the board. So we can say things with some authority based on their data, like if you get a high score in these DORA metrics versus a low score, you'll be spending 44% more time on new features than the low scoring teams. That's a huge impact in product productivity. One of the other outcomes of that research is that there is no trade-off between speed and quality. In fact, it's the reverse. If you want to be able to create high quality software, it's important that you move quickly, and it's important that you make change in small steps. If you want to produce software more efficiently, it's important that you build high quality into it, because otherwise the low quality, the impacts will hit you later on and slow you down later on. So this is the first time that we've ever had anything that's even vaguely scientifically justifiable in our industry that can point to concrete impacts of better scores. The DORA metrics they kind of work both ways around. If you get a high score, we can kind of predict what you're doing to achieve that high score. If you're doing certain things, we can kind of predict what your score is likely to be. That's a big deal. So one of the other outcomes of a high score on these metrics is that the business that you work in is likely to be making more money. That's a pretty important selling point.
Yeah, absolutely. I mean, one of the things you touched on is like you can't fake some of these things, like deployment frequency, for example, right? Like at the end of the day, you're releasing software, you're selling it to customers. If you don't have the processes in place to support, deploying multiple times a day, but you're doing it anyway, like it just wouldn't work for you as a business. Your software would just go down constantly.
Yeah. And even if it does help you out in the short term, it's not going to work for very long. It's going to come back to hit you real soon.
Yeah. One of the things that you mentioned that I wanted to just sort of like underscore was this idea that the DORA metrics under the hood, they're themselves a form of proxy metric. They're actually measuring batch size, or like the ability to drive down batch size. And that I think the authors even talk about it in Accelerate. It's just too hard to sort of like objectively measure batch size directly. So we move on to the 4 DORA metrics. I thought that was a fascinating point in the original book and in the Accelerate book, and one that I was really glad you mentioned.
Yeah. I think kind of, more colloquially, when I'm talking about continuous delivery and these sorts of practices, I often reinforce the vital importance of being able to make progress in small steps. And that, because it kind of crosses out. I see the 2 books that I'm primarily involved with writing, the continuous delivery book and the modern software engineering book, as being very closely related, in kind of the philosophy of software development. And this is one of the key things. I think that any great, I've been fortunate to be involved in some stuff that people have pointed to and said was good, in terms of software development. And I certainly, in my experience of anything that I've looked like, been personally involved in or seen from the outside that's been seen as great software, it's a process of incremental evolution of ideas and products. And so if software is about essentially evolving our solutions, we need to be able to retain the ability to make progress with some confidence when we don't know all of the answers yet. We're not quite sure what the direction's going to go in. So working incrementally is vital to being able to do a really great job, in my view, and sustaining our ability to get fast feedback over short cycles is one of the key tools that helps us to be able to make that kind of incremental development work. And so the DORA metrics are reinforcing that kind of thinking, I think.
Yeah, absolutely. One kind of follow-up question based on what you just said is like, when you talk a lot about sort of like the engineering practices that support managing complexity, and to me that connects really deeply to this idea of like iteration and moving iteratively. As an engineer, as someone like sitting down and writing code, how do you think about the right balance there, right? Like you kind of don't know all the answers. You have to commit to some decisions. At the same time, one of the concepts that you think about a lot when you're writing software is reusability, generalizability, abstraction. So when you're writing code, how do you think about like, how are you in practice supposed to make the sort of like the trade-off between working iteratively, working quickly, building out partial solutions, and sort of like future-proofing, building modularly, etc.?
My approach to design and development has been, has grown over a long period of time, and I can't point to all of the, directly to all of the things, but one of the influential ideas, it's not quite that it changed the way that I thought that I did things. It changed the way that I thought about things. Was the idea of domain-driven design. So domain-driven design. So domain-driven design is fundamentally, there's a lot of detail in domain-driven design in the book, but fundamentally the idea of domain-driven design is kind of what I thought object orientation meant when I first came across it. It's basically trying to find ways to model the problem. So rather than thinking about writing code, fundamentally I'm trying to model the problem, and I'm going to use code as the tool with which I'm going to model the problem, but I'm trying to find a way of modeling the problem that I'm trying to solve. And I think that helps a little bit. One of the other things that kind of came into my toolkit that I think is enormously important, and in the same class of the kind of ideas that we're talking about at the moment, is test-driven development. Test-driven development is one of the most important ideas that has come across in my time, I believe, in that it's a genuine engineering practice. If you practice test-driven development, I think you increase your chances of doing the kinds of things that you're talking about. So in my engineering book, I talk about 5 principles for managing complexity in the way that you were just describing. So we want modular code, we want code to be cohesive, stuff that's unrelated is far apart, stuff that's closely related is close together. We want to have lines of abstraction so that we can deal with other parts of the system without knowing or caring about how it works. We want to be able to have separation of concerns, so each part of the system is focused on solving one part of the problem and doesn't know about other parts of the problem. And we want loose coupling so that we can deal with these pieces independently of one another. Test-driven development is one of those things that I think is the closest thing that I'm aware of that we have to a kind of talent amplifier. We can kind of turn up the volume on our talent as a developer by practicing test-driven development. It's not going to make a bad programmer great, but it will make a bad programmer better and a great programmer greater. And so if you think about all of those things, we're going to write the test first before we've got any code in test-driven development. By definition, that's what we're going to do. So if we're writing the test first, we're going to want to make our own lives easier. And so we're going to want to make it easy to write the test. So what does testable code look like? Well, it's modular, cohesive, good separation of concerns, has nice lines of abstraction and loose coupling, because we want to be able to test pieces in isolation and not worry about the impacts of other things going on in our test. If our test is to be reliable, we want all of the stuff that's together to be together in the same place so that we can test it together. We want to be able to interact with other parts of the system without caring about how they work, so we can do things like mocking, so that we can isolate those things and just write to them. So all of these techniques are kind of amplified by test-driven development, and I think that's one of the tools. So we can start off not really knowing where we want to go in our design, and we can kind of come to the point of say, oh, I've got this idea, and I'll start writing some code, and then I'll realize actually now this means that the piece of code in front of me is doing 2 things. So separation of concerns, and say, well, let's pull one of them out. So we'll pull the second one out, we'll put that in a separate module of some kind, and now we can kind of test that boundary. And that gives us the testability, but we'll abstract the interface to that module, so we don't need to care about it too much. We know that this solves the problem, but we're not quite sure about where this is going to go in future. We don't have to think too far ahead, but we're facing the problem as we understand it right now, and we're breaking up the software into these more modular, more cohesive, more loosely coupled systems. And what that does is that even if we've completely screwed up and get that wrong, it's given us a few things. First of all, because of that approach to design, I think that our tests don't really know about the implementation detail of the system. They're just trying to, because we're doing test first, they're doing from the outside in, they're just trying to evaluate what that piece that we're testing is meant to do. So they can be abstract, so they're less likely to break when our implementation changes. If the tests break when your implementation changes, they're wrong. They're not well written. So we can kind of use that as a tool to kind of get there. When things go wrong, we can always screw up. We can always make mistakes. So it's possible that we might have to go back and revisit the test. It's possible that we might have to revisit the organization of our software. But all of those things are going to be easier to do if our software is modular, cohesive, loosely coupled, good separation of concerns, and all of those things. So we're less likely to hit those events when we have to, and when we do have to, making that change is going to be easier. Just for a moment, I would ask the people that are watching this, just for a moment, think about the system that you're very familiar with or that you're working on right now, and imagine it in two versions. One of them is modular, cohesive, good separation of concerns, loosely coupled, lines of abstraction, all of those good things. And another one is a big ball of mud, none of those things in any degree. And you've got a new feature to add. Which one would you prefer to add the new feature to? I guarantee that anybody that's written any software at all is now deeply preferring the first one. I think that's kind of what we would think of as, some principles that we could establish around what good means in terms of design. And so I think that they're not going to guarantee you the right answer, but they're going to give you a better chance of getting the right answer if you follow those thoughts. And when you get the wrong answer, it'll be easier to get it back to whatever you now think the right answer is.
Yeah. That resonates with me so much. One of the challenges I've always thought of is when I think about design is it does feel like so much experience and art. You know what I mean? Like measuring modularity. Like there's no quantitative way to look at a system and assess its modularity. Do you think we'll ever get there or get in that direction, or do you think we have to accept that it's a bit more art and experience driven in terms of recognizing it and applying those types of patterns? Maybe art is the wrong word, but sort of like experiential plus, like a skill based activity.
I prefer your second version. I prefer talking about it as kind of, experienced, maybe even talent or skill, that you apply to these things. And I'm not saying that only experienced people are talented or skilled, but certainly those sorts of things rather than art. And the reason that I think that I make that distinction is that I think that often when we talk about art versus engineering or science or things like those, I think in the back of people's heads is a wrong idea, the wrong meme, which is that art is all about creativity and engineering or science is all about some kind of a bureaucratic following of rules. And I think that's nonsense. I think I think of myself these days as an engineer. I think if you look at the world, the height of human creativity is engineering. I would argue, look at the internet. The internet is an artifact of engineering. The International Space Station is an artifact of engineering. The telephone system, the mobile phones, all of those things are acts of engineering. They are hugely creative things. The difference in the creativity that engineers pursue, or scientists, and that artists pursue, is that the engineer and the artist are constrained by reality more. Sorry, the engineer and the scientist are constrained by reality more, in that our stuff has to work. So I can draw a picture of stuff, I could be like Escher and draw a picture that doesn't make any sense at all, in reality, and it's a lovely picture and all that kind of stuff. But it doesn't have to work. I don't have to be able to build a walkway like that. But if I'm engineering something, it's got to work as a starting point. And so we are being creative within constraints. And so applying those constraints to steer our creativity is a good way forwards. So I think that's true. The other aspect of this is that I think that we have a kind of an illusion of engineering in other disciplines sometimes, which is that it's kind of some sort of bureaucratic cookie cutter process. And again, I think that's completely wrong. I think that's completely a misguided view of what engineering in practice is. And engineering is about optimizing to have the greatest chances of success in other disciplines. So we're going to apply science and those sorts of constraints that will steer us away from the dumb ideas, the ones that are definitely not going to work. And then we've got to be creative within those bands to find the ones that do. So partly it's true that it takes some individual creativity, talent, artistry maybe, but experience, skill, whatever it might be, to be able to achieve a good outcome in engineering. That's certainly true, but that's true in any form of engineering. It's not really. So I don't like the term art, which is why I preferred your second description. So we're working. I think that what we can do, I think the mistake that we make if we give up on the idea of engineering. I'm not anti the software craftsperson movement. I think there are some good ideas and I think it was a very important step, but I don't think it was a step far enough. And I think that engineering is the next step that takes us beyond that. And so I want to keep all of the creativity and so on from a craft-based mindset to doing things, but let's put the constraints in place. Let's say, what I would, if I ruled the world of software, what I would do is that I would say, okay, we're going to use the ideas of modularity, cohesion, separation of concerns, coupling, and abstraction as definitions of quality for our system. And we're going to work to amplify those whenever we do work at whatever scale. So those are some guide rails. If you've got two choices in your software and one of them is going to break the modularity or reduce the coupling, that's a point at which you're challenged. And if you've been doing good engineering, you're going to try not to do that. You're going to do your best to avoid that in all circumstances. And I think that if you followed that kind of rationale and those kinds of rules, you're going to build much better systems more efficiently. That's my belief. That's what I think one of the outcomes of what the sort of stuff that the DORA metrics are saying.
Yeah, so, I agree with you completely. I think one of the challenges that I was trying to get at, though, is like oftentimes when, let's say, two highly skilled engineers with a ton of experience in building, modular systems are reviewing a piece of code, they'll look at it and sort of say like, well, the design would be better if the following refactoring were applied. And, then there might be a disagreement from the other experienced engineer. It's sort of like, if it is an engineering discipline, you want there to be objective rigor that can be applied to like choices, in terms of like one design versus another. And without getting into the fallacy of getting into bridge design metaphors, I want that to be the case in software engineering. And too often it appears like in those types of discussions, it's difficult to remain completely objective, and things go into a little bit more subjective, like is design A better or is design B better? And that's sort of the direction that I was approaching this from why.
Yeah. So obviously that would be nice, but I think that would be a different thing. And I don't think you asked me at the start whether I thought that was going to be achievable. I don't think that level is going to be achievable, because actually I don't think that's it. In reality, I don't think that's engineering. Mm-hmm. The reason that I don't is think about. So one of my favorite examples of world-class engineering that you can kind of watch on YouTube at the moment is Elon Musk building his Starship in Texas. So they're building here a kind of spaceship that's never existed before. That's a quantum leap, really, in forwards in space travel, if they're able to achieve it. And they're experimenting and they're trying out ideas all of the time. And it's every single week there's a new change, there's a new idea, there's a new thought that you can see visibly from people half a mile away taking pictures of it. So they're experimenting on this grand scale. One of the experiments that they did, so unusually for a spaceship, the spaceship is built out of stainless steel. And there's all sorts of interesting reasoning that went into that choice, but that's what they chose. At one point, so they built the hulls of their spaceship, which are also the containment vessels, so pressure vessels for the rocket fuel. And they built it out of 4mm stainless steel of a particular grade in which they knew the tensile strength and they could measure all of that stuff. So they'd done all the maths. They knew what the theoretical limits of all that was. And then they decided that they could save a huge amount of weight across the whole space vehicle if they changed it for 3mm steel instead. And they did all the calculations, and the tensile strength of this stuff is perfectly known. But nevertheless, what they did is they built a little test rig, and then they went and blew it up and see what the actual tensile strength was of the vessels that they could build in their circumstances. So one of the things that I think distinguishes engineering from science or maths, which are critical to good engineering, but one of the things that distinguishes it is it's empirical. It's in the real world too. So in your example, you've got two experienced, talented, qualified, good, capable engineers, software developers working together. And they can't agree on the solution. That's because there's no one right solution. That's always going to be true. And so what would you do if you're being rational, experimental, trying to apply engineering thinking? Well, the first thing is could you evaluate the difference between the two ideas in some kind of test piece? Could you do a little experiment that tried it out and see which one worked better? Could you do a little piece that just gave us a sense of whether one solution was more modular, more loosely coupled, better abstracted than the other? Measures of that are probably somewhat subjective, but if we started adopting this as a discipline, they would become less subjective. We'd start to agree more reasons why what we meant when we said that kind of thing. So if we could do all that kind of stuff and then try it out, the engineers could then agree on which is the better solution in an ideal world.
Yeah. I think that's a great segue into a slightly different topic around feedback loops. Like, I think in that scenario, that's how it plays out in practice, right? You sort of like you pressure test two designs, and you sort of say like, well, if we were going to extend the system in this way, how would the system react? That's a sort of like empirical evidence-based gathering. I think one of the challenges is if you go the extra step and you actually build one solution and deploy it, your ability to sort of get feedback on modularity, sometimes that's quite a slow feedback loop, at least in terms of like in comparison to say, releasing a change and seeing whether the audience or your customer base, uses it, adopts it, etc. Like you have to wait for a refactoring cycle, extension, or whatever, which could be very slow. But I think that's a great segue into the concept of like feedback loops and their importance in the software development practice. What are some of the, I guess if you think about the software development lifecycle as a pipeline from like developer desktop to production and then that feedback loop, what are the spots where you see opportunity for improvement? What are the spots where the feedback loops seem inefficient or slow, or where you see a practice that in your own experience should be used more broadly by teams and isn't being used?
So I think that for most software development teams, there are usually opportunities almost everywhere across the board. And there are different organizations will probably be best to focus on one of those things first. The commonest ones that I see, so I spent the vast majority of my career building real software systems, usually, for want of a better description, at the slightly more complex end of the scale, sort of bigger distributed systems. So that's largely what's in my head when I'm thinking about it. I'm usually thinking about bigger scale systems. But these days I make a living consulting with organizations and advising them on how to do exactly what you've just been describing. How do you optimize your process? And the commonest starting points that I see are usually the requirements process is badly broken. It's usually not a requirements process. It's in the vast majority of certainly larger organizations, requirements are more like remote control programming. There's somebody telling the development team what things to do precisely, add a column to the database, make this bit faster or something like that. And that's wrong. That's not what, by definition, that's not what requirements are. Requirements are a description of what a user wants of the system. Mm-hmm. So that's an important thing to fix. And if you can fix that, what it means is it's much, much easier then to be able to define what you want of the system. So you can start then coming up with some examples that would demonstrate that requirement was met. Those are your acceptance criteria. Those are your executable specifications that will drive the development process. So then that gets us to the next testing. So the next idea, which is testing. Testing is usually too late in the wrong part of the organization. It's usually, certainly in bigger complex systems, often it's manual. So it's slow, ineffective, low quality, high cost, not very reliable, not repeatable. So by bringing these forwards and we create an executable specification for what it is that we want, we kind of bring that to the front of the process rather than the back. Edwards Deming, the guy that kind of was the grandfather of lean thinking, said that you don't inspect quality into a process, you build it in. So we can't make a high quality process by looking at it after we think we've finished and saying, oh yeah, there's a bug. We have to build in the process of finding the bugs earlier into the process. In continuous delivery parlance, we sometimes talk about that as shift left. We want to bring everything forwards, but fundamentally, so if we could start off by creating an executable specification for the behavior of our system that said what it should do, that would be a better place of organizing. So the testing strategy, the testing approach is another place that is very, very commonly wrong. One of the things that's wrong about that very often is who's responsible for it. It has to be in the development team. It can't follow on afterwards because that's too slow, too latency, lead to bigger batch sizes, all that bad stuff that we were talking about earlier. So it has to be in the responsibility of the development team, and fast cycle, short, simple to do. And you need to apply clever ideas to be able to do that efficiently. Then there's the development. So developers, the place in which development is often wrong is in two areas primarily. It's the coupling between teams as organizations have scaled up and the approach to testing. So development teams at the lower functioning end of the spectrum, for want of a, that's very rude, but I can't think of another way of saying it right now. So I'm not meaning to offend anybody, but at the lower end of the spectrum of doing these kind of things, developers are not willing to take responsibility for testing their software. They're hoping that somebody else is going to do it afterwards. That doesn't work. It doesn't work very well. It works a little bit, but it doesn't really work if you're building high quality systems or high performance systems. So we want to bring that into the team, that responsibility. So test-driven development, those sorts of techniques become ingrained in the way in which we approach work. And if we're getting to do that, what we need for testable systems is more deterministic. So there are changes in the development team. We want those teams to be autonomous, work independently. The second part of the problem for development teams is coupling between the teams, so that if I make a change and you make a change and our changes depend on one another, are we allowed to release them independently of one another? Have I got to wait for you to finish before we release our changes together? Have you got to wait for me to implement a particular feature that you're depending on, and so you're stalled? There are all those sorts of complexities that spin out from teams being organized in the wrong way, and the visibility of their changes not being aligned with what we're trying to push into development. So determining the scope of evaluation in the deployment pipeline in continuous delivery, for example, and understanding the scope of teams work is vitally important. The outcome of that, one of the ideas, the other ideas that we haven't mentioned at all, which I am a big fan of, is the idea of team topologies. The book that Matt Skelton and Manuel Pais wrote a couple of years ago, which describes using the organization of teams as a tool to structure development. Team Topologies is a great book. I recommend it to anybody interested in software development. But that allows us to design more effective teams that are more loosely coupled from one another. One of the weird things about all of this stuff is that teams and the human process is an information system too. So all of the stuff that's true about software is also true about organizations and how we structure them. So we want to reduce coupling. We'd like the organizations to be modular and decoupled from one another and have lines of abstraction between them. And all of those things also apply to team design. And Team Topologies talks about that. Not in those terms, but that's the way that I interpret what it's saying.
I haven't read that.
Yeah, and the last bit of the puzzle that nearly always trips people up is managing the infrastructure. The infrastructure as code, DevOps operations, SRE, those kinds of ideas, all of that kind of stuff of how we get it the last leg into production. So optimizing that process, so making sure that there's little variance in the infrastructure, so that as far as context of our product or our system allows us, we're going to take complete control over all of the dependencies that our software is related to. If you are running software as a system, then I think the right strategy is to make sure that every bit and byte is the one that you intend it to be, that every bit and byte you put into production is the one that you mean it to be, and that you've tested it pretty much. If you're working in, if you're building an app on a mobile phone or standalone software on a computer, then maybe it's a little different, and your job then is to just keep yourself loosely coupled from the infrastructure so that your software can change without being killed by the changes to the infrastructure. But managing that is also a crucial part, particularly in bigger, more complicated systems, but for any system really. So I think those are the common points. Those are the commonest places to look. And then there's lots of wrinkles and nuances about how you address those and how you get people to change their minds and all that kind of stuff.
Awesome. That's incredibly helpful. Yeah, these are practices that I think are essential in modern software development. You mentioned infrastructure as code, test-driven development. Definitely some of the things that are really indicators of high-performing teams.
Yeah.
I think we are just about at time, right, Jessica? So, Dave, I want to thank you for the amazing conversation.